Designing safer plastics, integrated discovery and evaluation of non-estrogenic bisphenols for sustainable polyester materials. Bisphenol A, BPA, has long been a cornerstone monomer in polymer manufacturing due to its favorable thermal stability, durability, and processability. However, its well-documented endocrine-disrupting activity necessitates the development of safer alternatives. This video describes an interdisciplinary strategy for the identification, synthesis, toxicological assessment, and polymer integration of non-estrogenic bisphenols. By combining computational modeling, green synthetic methodologies, in vitro toxicology, and polymer science, a library of candidate molecules was screened and refined to identify bis-guaiacol F, BGF, and related structures as promising BPA substitutes. Subsequent incorporation into polyester systems demonstrated comparable thermal performance with enhanced flexibility, highlighting the potential of these materials within a safe and sustainable by design framework. The widespread use of BPA in polycarbonates and epoxy resins has raised significant health and environmental concerns due to its interaction with estrogen receptors and associated endocrine disruption. Increasing evidence indicates that many structural analogues of BPA exhibit similar biological activity, leading to so-called regrettable substitutions. Addressing this challenge requires a holistic approach that integrates molecular design, toxicity evaluation, and materials performance early in development. This study adopts a multidisciplinary workflow to develop non-estrogenic bisphenols derived from renewable feedstocks, aligning with emerging principles of sustainable chemistry and materials innovation. Molecular design and in silico screening. A virtual library of 172 bisphenol candidates was constructed, with an emphasis on methoxylated, electron-rich aromatic systems inspired by prior observations that such structures exhibit reduced endocrine activity. Computational evaluation was performed using a predictive model trained on estrogen receptor alpha, EER-alpha, agonist and antagonist datasets. Candidates were ranked based on predicted estrogenic activity, with priority given to molecules positioned near the Pareto-optimal front of low agonist and antagonist responses. Additional selection criteria included synthetic accessibility via catalytic routes and the feasibility of sourcing precursors from lignin-derived renewable feedstocks. Catalytic synthesis of bisphenols. Selected candidates were synthesized using environmentally benign catalytic strategies. Two primary routes were employed: Lewis acid catalysis. Moisture-tolerant zirconium or hafnium catalysts enabled Friedel-Crafts-type alkylation of benzylic alcohols with electron-rich arenes under near-ambient conditions. This approach minimized energy input and eliminated the need for stoichiometric dehydrating agents, producing water as the sole byproduct. Brunstad acid catalysis. Conventional acid-mediated condensation was used for more substituted derivatives. Reaction optimization included the use of renewable solvents such as 2-methyltetrahydrofuran and tuning of catalyst loadings to improve efficiency and reduce waste. Several products were obtained as regioisomeric mixtures, which were separated where necessary for biological evaluation. Catalyst recyclability was demonstrated, reinforcing the sustainability of the synthetic methodology. In vitro assessment of endocrine activity. The synthesized bisphenols were evaluated using two complementary in vitro assays. MCF7 proliferation assay assesses estrogenic mimicry by stimulating the growth of human breast cancer cells. VM7 LUC4E2 reporter gene assay measures estrogen receptor-mediated transcriptional activity. Test compounds were evaluated across a wide concentration range, 10 to the power of -12 to 10 to the power of -4 mole. Estrogen, EE-E2, and BPA exhibited the strongest biological responses, while most synthesized candidates showed negligible activity. Estrogenic potency was quantified relative to E2, with values exceeding 20% considered significant. 3 candidates, bis-guaiacol F, BGF, and 2 bis-4-methylphenyl methane isomers, demonstrated minimal to no estrogenic activity, validating the predictive power of the computational screening. Polymer synthesis and material characterization. Among the top candidates, BGF was selected for scale-up and polymer integration due to its favorable synthetic yield and safety profile. To facilitate polycondensation, BGF was converted into a bis-glycol ether derivative via reaction with ethylene carbonate. Polyester synthesis was achieved through polymerization with dimethyl succinate, a potentially bio-based diester, yielding a novel material, BGF-based polyester, alongside a BPA-derived analog for comparison. Molecular weight and structure. Size exclusion chromatography revealed that the BGF-based polyester exhibited higher number average and weight average molecular weights, as well as increased dispersity. These characteristics are attributed to the structural flexibility of the BGF monomer and the presence of regioisomeric mixtures, which influence polymer chain packing and growth dynamics. Thermal properties. Dynamic mechanical analysis and differential scanning calorimetry indicated that the BGF-based polyester has a lower glass transition temperature, Tg approximately 22 degrees Celsius, compared to the BPA analog, Tg approximately 33 degrees Celsius. This reduction reflects increased chain mobility and flexibility. Mechanical performance. Mechanical testing demonstrated that the BGF-derived polyester exhibits lower stiffness, but significantly higher elongation at break, indicating enhanced flexibility and ductility. These properties make it particularly suitable for applications requiring soft, deformable materials, such as flexible electronics, robotics, and biomedical devices. This study highlights several critical insights. Structure-activity relationships. Minor structural modifications in bisphenols can dramatically influence endocrine activity, underscoring the importance of precise molecular design. Interdisciplinary integration. The combination of computational modeling, synthetic chemistry, toxicology, and materials science enabled efficient identification and validation of safer alternatives. Sustainability considerations. The use of renewable feedstocks, green catalytic processes, and biodegradable polymer backbones contributes to improved environmental performance. Avoiding regrettable substitutions. Early-stage toxicological screening is essential to ensure that replacements are genuinely safer rather than structurally analogous hazards. Conclusions and outlook. The integration of predictive modeling, green synthesis, and biological evaluation provides a robust framework for the development of non-estrogenic bisphenols. Bis-guaiacol F emerges as a promising BPA alternative, offering reduced endocrine activity and desirable polymer properties, particularly in flexible material applications. Future work should expand toxicological assessments beyond estrogen receptor activity to include long-term exposure effects, degradation pathways, and life cycle analysis. Additionally, scaling and industrial processing studies will be essential to validate the commercial viability of these materials. This work exemplifies the transition toward safe and sustainable by-design chemical innovation, demonstrating how multidisciplinary collaboration can address complex challenges in modern materials science.